Since we're going to be plugging series into differential equations, we're going to need to know how to do some basic operations with them. So let's talk about arithmetic and derivatives of series. And I've called that just operations that we do on series. So if you have a series and you want to add or subtract like two different series, you're going to do that component-wise. And when I say component-wise, I mean by things that have the same power x. You just add them together. And usually that's just going to be whatever multiplies the x to power n, you add or subtract them. This means that we're also going to multiply and divide series the same way we would polynomials. We won't really be doing that. I just want to note that if you wanted to take product of two series, you would have to do like all their cross terms. It's a very complicated process. We might wonder like when a series is zero. So if you have an infinite series and you set it equal to 0, and you want that to be true for all x in the interval of convergence, then you're going to need c sub n equals 0 for all n. That can seem like kind of a weird thing that I want you to know, except that a lot of the time when we have differential equations, they either come or can be rearranged equal to 0. And so now we know that if we have a series representation of an ODE, and we set that thing equal 0, because there's a 0 in the ODE, then we need all our coefficients to be 0. This is going to be how we get rid of the whole series representation to give us something we can actually solve. And then when we take derivatives, which is going to be very important, we just do that like a regular power or polynomial. And it happens for each term. So if we have y equal to the sum from n equals 0 to infinity, c sub n times x minus a raised to the nth power, then we said that the written out version of this is that y is c0 plus c1 times x minus a plus c2 times x minus a squared plus c3 times x minus a cubed, so on and so forth. If I want to take a derivative of this right here, I know how to do that already. I've got y prime x would be derivative of c with respect to x is 0. Derivative of c1 times x minus a with respect to x is just c1. Derivative of this term, I have x minus a squared, so I bring out my 2. I leave my constant alone, and then I move down in power. You just treat it like a regular x squared term, or if that's not comfortable for you, this is a u sub type derivative. And then for the next one, I've got 3 comes out, and x minus a cubed goes down 1 power to 2. So hopefully you accept that derivative and can kind of see how you would get there. We actually have to take it one step further though, and we'd like that derivative to be represented as an infinite series, just like y, for when I plug it into an ODE. So I want it to be an infinite series, but my 0th term actually went away. So this series is going to start from 1. And then I still have my C's, like I have that C1, C2, C3. But now, here, I multiplied by 2 on my 2nd term because of that x squared power. And I multiplied by 3 on my 3rd term because of that cubed power. So it's actually Cn times n times x minus a. And then before, if I had power 1, it becomes power 0. If I had power 2, it becomes power 1. If I had power 3, it becomes power 2. Just a power rule. So my exponent becomes n minus 1. Y double prime is going to follow this same pattern. I lose another term. So I start from 2 now because when I take another derivative here, C1 is going to go away. And then I've already multiplied by n, but in the next derivative I'll multiply by n minus 1. And then my x minus a is going to go down 1 more power to n minus 2. And that's how we represent series derivatives in this section. So I'm going to switch pages on you. Hit pause if you're still copying down these formulas. But the reason we're covering this is because we will use these properties to plug series into our ODEs. We need to know y, y prime, y double prime, and to simplify our equations. I might need to add series or subtract them, so that's why I need to know how to do arithmetic on them. What we're usually going to be doing is shifting. We will be shifting series indices. That's the plural of index, indices, I-N-D-I-C-E-S. That's the number on the bottom of the series, it's its index. Which is going to let us turn sums and differences of series into a single series. If I want to do that, if I want to combine these series, I'm going to need two things. They're going to have the same lower bounds, that n equals 0 on the bottom, and they will have to have the same powers of x. Inside they have to have that same x to power n. If that's true, then you can go ahead and combine their coefficients. So we're going to do an example so that becomes a little bit more concrete, but just to give you an idea of where this is going, I'm going to flip back a page. Go ahead and hit pause if you're writing. But basically, I'm going to have a differential equation that has y, y prime, and y double prime. They're all going to have different lower bounds and different powers x. I'm going to have to manipulate everything that I plug in so that they have the same lower bounds and power x. The reason I want to do that is because my ODE is going to be equal to 0 on the other side. And if I want to make that true, I need to have it in a single series like this, where I have this fact that, okay, once it's like this, everything that multiplies the x's has to be 0 for it to be true. So all this discussion of how we manipulate series is really going to help us set up and solve differential equations later. To see our first example of that, I'm going to go ahead and pause this video, and then in the next one we will manipulate series to combine their coefficients.